Good afternoon, everyone. I'm Giorgio Veronesi, President of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for almost 8 years, and currently I'm in my second year as a president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects, mainly abroad, with several assignments overseas. I am very happy to be involved in the introduction of this webinar on opening chemical engineering to the power of open science, and I'm looking forward to participating to it. Let me say something about this webinar series. EFCE is organizing a series of virtual talks on significant topics in chemical engineering. This is now our 4th year of the initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced the management of EFCE to transform the Spotlight talk in a regular feature of our program. 9 of our working parties and sections, quality by design, multi-phase fluid flow, high pressure technology, chemical engineering applied to medicine, static electricity, early career chemical engineers, crystallization, characterization of particulate systems, loss prevention and safety promotion, thermodynamics and transport properties, are delivering over 2 weeks short session of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The series also enables attendees to sample matters in areas that they find interesting but may not otherwise have had the opportunity to attend before. In this way, we want to encourage cross-fertilization between specialist areas. Links to the next talks are available when you register in this event or via the EFCE website. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 of them in Europe. EFCE working parties and sections cover all major aspects of chemical engineering and are, in fact, at the core of the organization, forming the scientific engine that drives many of EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. I'm particularly happy that in this series of Spotlight Talks, we will have the first contribution of the 2 newest sections of EFCE, Chemical Engineering Applied to Medicine, and today, the Early Career Chemical Engineers that manage this webinar. Before concluding, I would like to thank all the people who work hard inside the working parties sections and EFCE in general for this initiative and to happen to be successful. And in particular, I would like to thank EFCE Martin Pou in Toulouse, who did most of the conceptual, setting up and practical activities. Thank you very much, Martin. So I thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. I would then give back the work to the chair of the Working Party on Early Career Chemical Engineers, Gabriele Verrecchia, to start the works. Gabriele, the floor is yours.
Thank you, Giorgio. Hello, hi everyone. My name is Gabriele Verrecchia. I'm the chair of the newborn EFCE Early Careers Chemical Engineering section. So today we stand here to shed the light on this invaluable opportunity that has the potential to transform the field of chemical engineering. It's the concept of opening chemical engineering to the power of open science. So the world we live in today is driven by innovation, collaboration, and is based on the unrestricted flow of information. By embracing open science, we believe we can unleash the full potential of chemical engineering and accelerate scientific progress like never before. So chemical engineering plays a vital role in our lives. It's responsible for developing sustainable processes, creating new materials, and finding solutions to pressing global challenges. However, the traditional approach to scientific research in this field has a bunch of limitations. Researchers often work in isolated silos, competing for limited resources, and struggling to access critical information. So this fragmented system slows down progress and hinders collaboration. Open science presents a paradigm shift in how we approach to scientific research, and it's about making scientific knowledge accessible, transparent, and reproducible. In this rapidly evolving field that we're living, it's crucial to stay ahead of the curve, and that's where our section come in. So our early careers community section is designed specifically for young professionals, providing a platform to connect, learn, and grow. By joining our community, you will gain direct access to a vibrant team of engineers, ambitious chemical engineers who share your passion for innovation and progress. I believe together we can explore the latest advancements, tackle industry challenges, and exchange valuable insights, both coming from workshops and webinars to conferences and industry tools. Our section offers a plethora of opportunities to expand your knowledge and expertise. So don't miss out this opportunity, and take a look at our website, efce.info Early Career CE, to learn more and become a member right from today. So now I would love to leave the floor to the first speaker, Pedro Mendes from the University of Lisbon. Thank you.
Hi, everyone. Thank you, Gabriele, for the nice introduction. I believe you can see now my presentation. So with the EFCE working party, with Gabriele and Laura, we organized this workshop on our spotlight talk on open science. And my role here is just to give you an intro of what is open science today and the clue on what is the landscape today. I think the examples that come after will be also very insightful, so I will not dig too much into any example. So what is the scientific motivation behind open science? So open science has been there for very long. Don't get wrong on that. For instance, for the periodic table, when Mendes put together the periodic table at the end of the 18th century, he gathered contribution on the discovery of the elements by many researchers. One of them was Sir Humphrey Davy, which, among others, has discovered sodium and potassium. For instance, Sir Humphrey Davy discovered this about 60 years before Mendes put together the periodic table. So the only way Mendes was able to retrieve these results and make the puzzle of the periodic table was by a very good quality and of information and the openness of this information. So in fact, Davy published a book with all experimental proceedings, the results, including the negative or failed results, as sometimes one would say. So this is the basis of open science. We also saw this more recently during COVID, of course. There were communities released everywhere. Zenodo is the main platform for data sharing in Europe, and also there are communities were created to have rapid sharing of data. I mean, I think we all remember that there was a possibility of studies being carried out in the morning, and we basically have the data at the evening news. So that was impressive, and that's really what open science is about. It's about breaking the barriers to knowledge and also improve science collaboration in that matter. As data is open, we can more easily collaborate. So how does this differ from what the current status? So the current status in science is that we have raw data, typically in a tabular format, but any other can be used. We do a step of information extraction, so understanding what is the information there, and we disseminate the knowledge that was taken from that information, and that typically goes as scientific papers, or but can take any other form. And this data goes to the trash bin. The trash bin can be archived files of an institution, but very often in publication is also supporting information. So in this way, we have in here data cycle with single-use waste data. What we aim at, what one aims at, is to close this loop and get to data circularity. To give you a few figures on this reality, here you can have a data set to scientific article ratio. So it's to give us a feeling of how many data sets are published per scientific article. And this is multiplied by 1,000, which clearly gives you how low the numbers are. So if you at the left-hand side, you can see various scientific fields. You have in purple the average of all scientific fields. So we have a 50 ratio, which is about 5%. So we have much less, 20 times less data sets as we have papers, average in all disciplines. And I took this till 2019 to also don't have any spurious COVID effect. But there's fields performing much better. You see biology, for instance, performs much above average, about twice. And you have other fields performing much worse. And that's chemical sciences is on average, but chemical engineering, for instance, is very much below average. In fact, all engineers, if you take now a look at the right-hand side, all engineers perform worse than the corresponding science. You can see here also for materials engineering, the same kind of effect. So as of today, we are not opening our science, at least in terms of data. The question is there a revolution on the way? Is this changing after 2019 and these figures? In some way, governments and funders are pushing for it. So the European Union is pushing for this in every research project coming from Horizon Europe, for instance, with a principle which is as open as possible, as close as necessary. So that clearly conveys that data, information, knowledge by principle should be open, but for confidentiality reasons, IP reasons, data can also be closed. And that as such is fine as long as this is justified and restricted to only the necessary data. We see that this is indeed impacting researchers. So 70% of researchers have experienced or have to follow a policy on data sharing in the last year. On the scientists, we also see change. So LURU, which is the League of European Research Universities, which is a frontline league of universities, has published a manual on open science, promoting in favor of open science as far as 2018 by now. And also researchers themselves answered for over 5 that they are in favor of research data being made openly available. So it seems like things are changing from both the side of the scientists, but also from the side of who is funding science and wants the data to be public. Beyond now public science, what are the benefits of open science? So we have economic benefits that also come from open science. Science that is public but open can be taken advantage by companies, but also by ONGs. We have also a reduction in the inequality knowledge gap by publishing science open. It means that people in poorer countries can have access to studies that, for instance, don't have the means to be performed there. And we also can promote citizen science, which is aimed at taking a further role in developing our democracies as well. In practice, what is the private sector doing in chemical engineering? So, as I said at the beginning, we'll hear very nice examples from Richard Baur and Teodoro Laino just later, but these are a few examples I also put on the table. So, for instance, AstraZeneca is publishing their trial results, anonymized of course, but they're publishing their trial results for almost a decade now, and here is their justification. So we publish results from all our clinical trials on public registers, regardless of the outcome, to support scientific advancement. So that's, as stated, the goal, support scientific advancement, but there's also another clear goal from a company here. It's to promote trust. If data is publicly open, data is published regardless of the outcome, you then can better trust a company which is showing all the data, not hiding any data from you. So this is a common problem in chemical engineering, other than pharma, and BASF is also doing the same for their agro-business. So here you can see a map which you can select to know where trials for a given crop were performed, the variety of the crop, what was the yield. So here the figures are maybe are relatively small, but you can see that the yield changed as function of the crop. You even know the name of the agronomist that was responsible for these results. So various companies are opening their science to build trust on customers and citizens, and I think that can be a main driver for other companies, particularly in chemical engineering, to do so as well. Finally, I would also like to give a brief word on open innovation. Many companies are promoting open innovation. This, as such, I mean, I think it's a relevant initiative, but this is not related at all with open science. Open innovation is about companies opening the doors to innovators from the outside of the company, opening the doors to ideas from the outside. But these ideas will be most likely at the end closed, as these are supposed to generate profit at the end, which as such is fine. It's just not open science. It's opening the doors to external innovation. So open innovation, as it's typically stated these days, is not open science. Just a warning there. What is the ecosystem, particularly in Europe, in terms of organizations working around open science? So there are three main organizations that I would like to tell you about. We have the Research Data Alliance. Research Data Alliance is a non-profit organization that was mainly funded by a few countries, among others, the USA, Europe, and Australia, to start work around open data about 10 years ago. This is constituted mainly by researchers, but there are also various companies and professionals from companies working here. Their main work is to deliver recommendations and supporting outputs to the sharing of open data, and this aims at the end at the community-driven open data infrastructure. So at RDA, anyone can constitute a working group, anyone can take initiative forward, and then is for the community to adopt this as their practice. Then we have the World Fair Initiative. This is meant worldwide and as a field-specific FAIR recommendations. So FAIR are the principles guiding the data publishing, and the goal of World Fair is to make recommendations that are field-specific, contrary to what has been done by RDA. And this will end up with a top-down converged open data infrastructure. So this will come from the top without authoritarian institutions, but they hope, World Fair hopes that this will bring a structure as such. Then we have YOSC Future. So YOSC Future is solely funded by Europe, by European Union. It also has works beyond Europe, but basically here the goal is to support anyone that would like to share their data openly. So they basically provide open data services. I mean, the ultimate aim is being the Google of data sharing. So basically, you just need to go to that website to share any data, know anything about open data. So it's at the end aimed at a more innovative and streamlined open science. Now, to finish with a few tips on what how data sharing can be done in practice. First, there's a rainbow of open science. I mainly discussed data today, but in fact, you can open up your science at any point of research, from the first beginnings, biblio research, through analysis, publication, and then outreach. And you have various platforms and means to do it. Then I want to just get back on what are the key principles to share data. And these are the FAIR principles, as I mentioned just earlier. So FAIR is about data being findable, so that's easily available on the internet, accessible, so you know how you can access this data and how you can use it in terms of copyright and so on. Interoperable, so that means that it can be used by any software, regardless, by any open software, and regardless also of your machine, and that is reusable. So data is well described in such a way that you could redo all calculations, or at the limit be able to reconstruct the data set. So the take home is that open science is really about breaking barriers to knowledge. It's not perfect, but I think it's an important way to to society, academia, and the private sector as well. And for the private sector, open science can increase confidence and boost innovation and make a difference by sharing your data. You don't have to share everything, share as much as you are comfortable. Thank you.
Thank you, Pedro. Thank you. So I would like to have a couple of minutes to ask for questions from the attendants. So in the meanwhile, I've got a question so that we take a look at any other wants to join us in the question and answer session. So the question is, thank you for the presentation. The question is, what do you believe are the top 3 blockers that could prevent the implementation of the open science to be fully implemented in our system?
I think there's first, thank you for the nice question, Gabriele. First, there's a cultural change that is needed for any person. Think about data management from the start. So to openly share your data, you need to think it before it's starting generating the data. Else you have too much work. So there's the cultural change on that, on planning data. So that's research data management. There's also the cultural change on the fact that in public science, you don't own the data, but the data is owned by the body that's funded the research, and that body being public, the data should by default, but not always, be public. And finally, we really need this infrastructure. So right now, if you want to share data, you don't know exactly where to share it, even though there are platforms. You don't know exactly in which format and by which standards to share it, because there are still not standards for every data. So we need a couple more years to wrap up this data infrastructure such that everything is indeed more streamlined and you know exactly where to share, how to share your data, and we all do it in a similar and useful manner.
Thank you, Pedro.
I will now move to Teodoro Laino. Teodoro Laino is a researcher at IBM Research in Switzerland, and we'll be talking today about enabling a data-driven future for synthetic organic chemistry with open data. The floor is yours.
Thank you so much, Pedro, and thanks a lot for the invitation, for being here with all the participants. So let me start sharing the screen, and then there we are. I mean, you should be able to see slides and myself. So I'll take it over from where we left with the previous conversation on open data to give a little bit of a perspective on one of the revolution that happened in, I would say, in the last 10 years, and mostly thanks to the openness of data in the space of organic chemistry. So I will be showing how the open data can be leveraged for advancing one specific field, in this case, synthetic organic chemistry, at different level, not only from a technological perspective, but also fueling and surfing one of the revolution in the space of machine learning. It's not a big surprise that actually machine learning requires data, and so all the consideration that we have been doing previously are absolutely relevant when you think of developing methodologies for training models in capturing specific behavior. And so I will give you an example how you can build, thanks to the open available data, you can build models that can capture chemical reactivity, and then you can use this model for even driving laboratories that are autonomous in the sense of being driven by robotic systems. So before I jump into the topic, of course, I always start recognizing that the work that has been done by all the team of people that was behind it. So each of them has been contributing to one part of the work, and I'm only offering my face for presenting the entire outcome. So we were talking before at the very beginning. I was trying to motivate this talk, mentioning the openness of data in organic chemistry. And so why is that such a crucial point if we want to develop technologies that are modeling the chemical reactions and up to a certain extent even predicting the outcome of a chemical reaction? Why are we bothering if actually the set of numerical equations that are governing the system of atoms, the reactivity of a system of atoms, is well known since almost 100 years and has been implemented in different computer programs. So why bothering about data if we can calculate these quantities? It's very simple, because the application of quantum mechanics in a problem like chemical reactivity, where the number of species is quite large and the sampling is very important for capturing the essence of the kinetics of the phenomena, is something that still today, with all the computational power that we have, is very hard to scale to a large number of chemical transformation. We can apply first principle for understanding the behavior of specific chemical system, but definitely what we cannot do is systematically explore millions or tens of millions of chemical reactions with quantum mechanical methodologies. And so it is crucially important that these millions or tens of millions of chemical reaction are actually made available with the publications that are done in chemistry. It is important that we convey as a community, as a chemistry community, on specific data sharing formats that can be used by people together when publishing their paper. I'm a strong supporter that actually, while it's a common practice in the machine learning community to always publish together with a paper code and data sets in order to allow other scientists to reproduce exactly the same work that you are presenting in the paper, I would really be incredibly happy of seeing one day every single paper in chemical science, chemical engineering, have together with the paper also specific data formats that are making available in a computing processable way all the information that is reported in the paper. So this today is still not possible. There are several initiatives that are collecting chemical reaction data, more or less leveraging the self-initiative of scientists. In our case, we started from one work that actually was initiated in 2012, and this is the reason why this revolution started more or less in 10 years ago. In 2012, there was, as a part of a PhD thesis, there was the development of a series of tools, algorithms for text mining chemical reactions from public documents. And so this was actually leading to the creation of a first data set, public data set of chemical reactions extracted from text. And so I'm really referring to information like the one that I'm reporting here in the lower part of these arrows that are then converted into chemical equations describing a transformation. So it's no surprise that once a data set consisting of approximately 1 million entries was developed, was actually made available after extraction from public documents. and we are talking about patents. So this is another topic that is also very important. Maybe I will mention a few words later. But as soon as this data set was made available, it's no surprise that we started observing the flourishing of a large number of initiatives that were leveraging that data set, exploring different machine learning models, technologies. So openness of data, it's probably one of the best fertile soils for then promoting the advancement and the development of different other components, even not necessarily connected with the data itself. And so for the sake of data, everything that you will be seeing in the next slides is actually relying on information like the paragraph that I reported here. This is a very short paragraph describing one chemical transformation is extracted from patents. The reason why we have been using patents is that patents are public document, and as such, you can extract at scale information from these documents without infringing terms and conditions that instead are normally living with documents published by publishers, basically. So all the information will then be related to similar type of text, like the one that you see here, related to extracted from patents. And this information is really the only information, chemical information, that we have been leveraging for connecting specific target molecule to their corresponding synthesis. So in essence, in a few seconds, what we try to do is to exploit this information, these paragraphs, for learning the chemical reactivities, for learning how to put together successful experimental protocols for running chemical reactions that are not necessarily trying to reproduce what was already published, but even that are completely novel and not present in the data set. For this design, this complete synthesis of target molecule, we will be looking at two steps. So the very first part is the synthesis design, which is very well known as a retrosynthetic analysis. And then the second part instead is the one where every single step of the retrosynthesis is converted into a series of instructions and operations. These instructions can be executed by a human operator in the lab, but they can also be executed, previous conversion into actions by robotic systems. And this is what I will be showing you towards the end of this presentation. Now, let's start from the machine learning part. How did we use the data extracted from patents? So the approach that we tried to follow was very original. We did this work back in 2018, the very first one, and then continued for the subsequent 4 years. And this is actually a chemical reaction. And it's not a big surprise that if we look at the paragraph describing this chemical reaction, we identify that paragraph like a language component, a text that belongs to a specific language. In that case, English, natural language, that is that has the purpose to transmit information to people. But even the symbols that we are using in a chemical reaction are actually a domain-specific language, a chemical domain language. And so the parallelism that we try to draw between this chemical reaction and language tasks was that you can consider all the set of molecules belonging to the precursors, so to the left side of the arrow, as a sentence in a specific language that we, for convenience, we can call language of the precursors. You can also identify the product, one or more molecules that are belonging into the right side of the arrow, like a second language, a second sentence into a different language, in this case, the language of the products. And so the arrow or the chemical transformation can actually be seen like a translation between two different languages, the language of the precursors and the language of the product. Now, operating these similarities can be very cumbersome, very difficult if we stick to the Marcus structures, so to the diagrammatic representation of the molecules. But if instead we convert this into a linear representation, so in this case we are using smiles, but you can adopt different other types of representation. Well, then in this case, I mean, you can easily see that this is a sequence of alphanumerical characters that is translated into another sequence of alphanumerical characters. Now, from a technological perspective, this is an hypothesis. If this hypothesis holds true, then we should be able to use the same type of architecture that are used for translating between natural language, like between English and Portuguese, or English and Italian, French, and so on. And basically, being able to train an architecture that is capturing the chemical reactivity rules. And so this is what we did. We have been using back in 2018 the transformer architecture, and most of the machine learning revolution in the last years, not only in the chemistry space, but quite extensively in chemistry, but even in other disciplines, is pretty much driven by the transformer. So this type of language models that we were discussing and we were applying in the chemical context back in 2018 are very popular, for instance, today with technologies like ChatGPT, where the T stands exactly for transformer. So in essence, we have been using a transformer architecture. We have been using the data, the open data, chemical reaction records extracted from patents, to train a neuronal machine translation architecture that was actually doing a couple of tasks. The first tasks that was learned by the architecture was the one of absorbing and learning how to represent smiles. So learning, in essence, the language of smiles, which is the linear format that we have been using in our works. But the second task, which is probably more interesting from a chemical perspective, is the one that these architectures are capable of learning also how the atoms are mapped between precursors and products. And these are, in essence, the chemical reaction rules, the chemical transformations. So it's actually a very interesting concept, because you can reconstruct the same rules that have been rationalized in chemistry textbooks across the last 200 years by just taking one machine learning architecture and a couple of millions of chemical reaction records. There is no codification of chemical transformation. And this type of architecture based on the transformers are still today state-of-the-art regarding accuracy performance in forward reaction prediction. And if you had a little bit of experience with technologies, language technologies like ChatGPT, this is, in essence, very similar, with the only difference being that instead of asking a question in natural language, you are basically inputting a sentence with a smile notation. So now we know how you can do the forward reaction prediction. This is a translation task, but how do we do the retrosynthetic analysis? In a very similar way, in which you can translate English to French or French to English. Here we can build a retrosynthetic model by simply inverting the order of the precursors and product. So if you have your data set of a few million chemical reaction records, you can simply invert the order between precursors and products and then train an architecture. And the training of this architecture will actually be leading to a model that is capable of recommending single-step retrosynthetic disconnections. So retrosynthesis is also done. Then once you have a single step, it's a matter of exploring the tree. But in that specific context, there are already well assessed and established technology for exploring hypergraphs. Now, this last part is you have the design of the synthesis, you have a retrosynthetic analysis, but still this is quite far from really implementing every single chemical reaction in the lab. What is missing is the exact experimental protocol that is required for every single step of the retrosynthesis. And routinely, this is performed today by looking at templates, reaction templates, similarities between reactions, and looking in a database, and then trying to combine all the outcome of the search in a way that makes most sense to our chemical intuition. So instead, what we did was following a slightly different approach. But the very first thing that we had to do was actually build a data set of experimental procedure. Because if a data set of chemical reaction was publicly available, we did not have available a public data set of experimental procedure. And so what we did was actually extracting the paragraph from the patents and then training a language model very similar to again, GPT. Today, I'm sure you can actually do exactly this task by zero-shot learning with simple prompt injection, most likely. But at the time, in 2020, we were actually training a transformer that was taking a text and converting this text into coincide actions. We did that for roughly 1 million chemical reactions extracted from patents. And then we had a resulting data set, which we made available of chemical reactions and corresponding procedures. And so what we do with this data set of chemical reactions and procedure? We trained an additional transformer that was taking as an input an entire chemical reaction. So not only precursors or products, but actually the combination of precursors and products. So in essence, this string here, and was trained to reproduce in output the sequence of actions, the coincide sequence of actions in which we were replacing the name of the smiles with specific tokens, placeholders, this to account for the fact that inverting or commuting the order of the molecules in the set of the precursors is actually not changing the result of the chemical transformation. So this served actually also as an augmentation strategy for the data itself. So we had a one machine learning model based, again, always on the transformer that was able to, given a full chemical reaction, generate the corresponding set of instructions that were required for running the chemical transformation. And together with the set of instruction, also the corresponding properties of the instruction, like for instance, steering at a certain speed and temperature, or for a certain amount of time, and so on. So in essence, what we were able to do was actually capturing with this model all those macroscopic descriptors, like the thermodynamic of a chemical reaction, the kinetic of a chemical reaction, the formation of precipitates because of insolubility of forming molecules inside the reactor, or the separation of phases because of the sudden immiscibility between the different phases in the reactors. And we were able to trace back these descriptors, which were completely implicit. We did not annotate this descriptor for the chemical reactions, but we were able to trace back them to the presence of specific functional groups. So the model was in essence capturing the signal, which was connecting, correlating the presence of a specific functional group with the corresponding actions of the procedure. So what we did then afterwards is putting everything together with a software that is actually driving the entire experience, from people drawing the target molecule that they would like to synthesize, to the use of the models for retrosynthetic analysis, for the prediction of the experimental protocol, and then all the way to the execution on an automation hardware, and then monitoring the hardware itself remotely. And so for the hardware, we have been using something which is relatively standard, so batch reactors, 6 batch reactors with the possibility of handling liquid and solid. And these reactors were also coupled with analytical instruments for providing a feedback loop, both to the AI, but also to the operators. And this is in essence what you can observe from the camera inside this automation system. This was a very simple synthesis of a precursor for the creation of a photoacid generator. And yeah, again, that's exactly what you can experience remotely instead of performing those operations manually. But the synthesis of these compounds, for instance, was entirely driven and programmed with the machine learning model. I'll go very fast just to wrap up. I mean, what else can you do if you have open data and you have cool machine learning technologies? Well, you can use the machine learning for developing strategies for curating data sets. So for instance, here you can capture the signals of learning and forgetting specific type of data set records to understand which data is an outlier in the main distribution of your chemical reaction records. And so you hope to identify by applying this statistical analysis all those records that are noisy, that have been extracted bad, or that have even been reported wrongly in the documents. You can also use look at the machine learning model and extract a feature vector and use this feature vector for plotting atlas of chemical reactions. But you can use the same feature vectors also for training models for chemical reaction yields. And these are all things that we have been exploring quite well. So the amount of opportunities, if you have data available, combined with a little bit of creativity on the machine learning side, is actually quite tremendous. And finally, this is probably one of those things that are even philosophically very, very interesting, is that you can look at all the millions weights of the transformer and extract from these weights informations that were completely not annotated, not provided during the learning phase. This is an example of extracting an atom mapping algorithm from a trained transformer. And it's very fascinating how, without providing atom mapped reaction, the transformer is actually able to capture how the atoms are moving between precursors and products. You can also extend the same concept to enzymatic catalysis. So it's only a matter of having a proper representation for the enzymatic side. And you can even recover by doing so and having quite a substantial amount of open data in the space of enzymatic catalysis, metabolomic data. This is another field where people are very sensible to sharing actually data. By using the data, you can also train the transformer to identify in an entire protein sequence what are the amino acid segments that are connected to the active site of the enzyme. And in this case, open up the possibility to provide functional information for uncharacterized sequence of proteins. So I'll stop it here. I would like to thank you very much. And if there are any questions, I'm happy to address them. Thanks.
Thank you so much, Theo, for your very nice talk. I think you gave a very clear overview of all the potential of AIS for organic chemistry, but also much beyond that, of course. I'll kick off with a quick question. I mean, one could infer from what you just showed us that AI is already interpretable, but there's a lot of discussion on this. So can you comment on this?
Yeah, no, definitely. No, it's, I would say that we cannot arrive to a general statement about interpreting any type of model. The experience that we have is that if you are lucky and the data that you have allows, then for few specific tasks, you can be enough creative to put together a way to interpret the outcome of some architecture. I mean, with the transformer, for instance, and the atom mapping, I must confess that we have been relatively lucky. We were not expecting that, and the entire task has been very tedious, but at the same time, very rewarding. This is not a general statement. I will not arrive all the way to say that you can always interpret, even within the same model, within the same transformers, but different tasks, you can arrive to an interpretability. So I tend to agree with the common thought of the colleagues in the scientific community that interpretability is still a big challenge. But again, in few cases, we can be lucky.
At least it's worth trying, I guess. Okay, thank you very much, Theo. Thank you very much for your time. In view of time, I think we'll move forward to Antonio Del Rio. Thank you again, Theo. Antonio Del Rio is a professor at the Imperial College London at the United Kingdom, and is here today to talk us about data-driven optimization in process engineering. Thanks, Antonio, for accepting our invitation, and the floor is yours.
Thank you very much, Pedro, for the nice introduction, and you know, to you and to the EFCE for the nice invitation to talk about some of the things that we've been doing. So let me just get my pointer going. So the idea of this is that I wanted to talk about data-driven optimization. A quick recap. So I am a quick introduction. So I am a lecturer, like an assistant professor, like Pedro said, at Imperial College. The name of my group is Optimization Machine Learning for Process Systems Engineering. So the idea is that we try to use the algorithms from optimization, machine learning, and tailor them to the chemical industry, right? That sometimes means that it's adapting algorithms that are out there or creating our own, and these are the areas in which my group works on. And today I'll be talking particularly about data-driven optimization. So before I begin, just a quick commercial. So along with Pedro and several others, we're giving a machine learning summer school or specialization course, machine learning for chemical engineering. The idea is that it's an in-person course, and we'll be running it in September. And for anyone who's interested, there's a link. We can also supply it in the chat. But just a bit of a commercial where people that are interested in this area can learn this kind of things. And here is a bit, I mean, all the information is on the website, but this is the idea of the course. Okay. So what I decided to talk about today, in line with data science, is an online book. It's like a compilation of tutorials that I was invited to by Edgar Sanchez Medina. So Edgar is a researcher at the Max Planck Institute. He did a master's here at Imperial College, and he basically invited me along with Caroline Ganser to write. We have it as an online book. Let's say it's freely available. Anyone can access it here, where we try to put examples of how machine learning can be used in chemical engineering, right? So we have a few examples. We have things like supervised learning, hybrid modeling, data-driven optimization, reinforcement learning, and unsupervised learning. And obviously, there's so much material out there, right, on these topics. But what we felt that, I mean, there is obviously material on it, but something that we thought we could contribute is making specific all of these techniques specifically apply to chemical or process engineering. And it has codes and particular examples. And that's part of what I wanna talk about today, again, in line of the open science topic. So first of all, I wanted to give a brief introduction about what do I mean by data-driven optimization, because different people mean different things, and just to get everyone in the same framing. So a big picture idea, right, of what is data-driven optimization is, imagine that you have some kind of chemical process, right? But then you want to model it, and maybe this chemical process is a reactor, right? Where you have maybe some temperature here and some pressure here, and you want to find the optimal operating condition of this reactor, right? And this optimal operating condition can be, anything from maximum product to less, good product with less environmental impact, to most profitable, and so on, right? And this is the objective function, basically, where this is just best operating point, and this is the best operating point. These two plots are the same, only one is in 3D, one is in 1D. Okay, so again, assume that you have a chemical reactor, and again, generally people build models and so on, right? But there's many cases where this either is difficult, or I don't want to say it doesn't make sense, but there's better solutions to it, right? Like data-driven optimization. Anyway, let's assume that we want to optimize this function, which is actually some kind of reactor, right? But the problem is that we don't have we don't have this function form, right? What we can do is we can use different operating conditions for pressure and for temperature, right? Have the reactor stabilize, and then tell us, okay, what is your performance, right? How much are you producing? What's the profit if we operate it like this for 3 years or something? So the idea of data-driven optimization in this context is that you can initially have some number of samples, right? So you have these samples over here that you sampled from your function or your process, and you want to get, again, to this goal, right? This is where we want to get at, right? So what data-driven optimization does, or the idea behind it, is that how to get to this point, yeah, when we do not have derivatives, right? So we don't have the function. That means that we do not have derivatives. For people trained in optimization, you know that generally to do optimization, you apply derivative methods, right? But again, if this is a real process, or for example, design of experiments, right? Again, depending on what kind of the design of experiments you're talking about, but many times you don't have derivatives, right? But you can only sample this, right? There's also a very famous area now called reactor optimization, for example. And yeah, so anyway, the main point is that you have some samples here and you want to get to over here, right? So the idea is that we want to get there as efficient as possible, right? Because maybe, you know, doing experiments is expensive, right? Or changing an operating point in a process is expensive, right? Again, all of this is in a simplified case, right? Like there's many ifs and else that go into this, but just bear with me for now, just a simplified example. So again, you have these initial points and maybe you decide that this is your next best point, right? And the idea of data-driven optimization is that you intelligently sample, right? Until you make your way to the optimal, right? Again, in as few iterations as possible. Yeah. You know, there's a lot of, like just in the realm of data-driven optimization, there's lots of different things that you can think about, right? So for example, you don't know the function, right? So is it exploration or exploitation what you want? You don't really know the form of the function, right? So when you sample, it can be this kind of function, this kind of function, this kind of function. So you don't really know, right? So there's many nuances to this kind of algorithms, right? You don't know if your function is random or if it has constraints, right? If you're dealing with reactors, generally you have some safety constraints. You have many safety constraints. But so this is the idea, right, of data-driven optimization. And some examples, just to not, you know, not to say that it's actually catching up quite a lot, right? That people are really using it. Something that they use it for, and my research group is currently working on it, for example, is the use of how do you optimize expensive simulations, right? So if you think about it, for example, if you want to integrate some computational fluid dynamics, this is an expensive simulation, right? And if you want to optimize something doing that, this is something that if every simulation takes to you, let's say 12 hours or 15 hours, right? How can you actually get a good reactor design within some time frame, right? And most of the time you don't have access to derivatives. There are ways in which you can have access to derivatives, like adjoint methods. I'm not really going to go into the details, but again, most of the time you don't have derivatives. Again, design of experiments is a very typical example. There are other expensive simulations, such as molecular dynamics, right? There's also data-driven control and reinforcement learning these days, and things like controller tuning, which I'm actually going to talk about this later down the line. Okay, so very briefly, you know, you want to do data-driven optimization. So what are the types of algorithms that exist out there, right? So there's mainly three types of algorithms. Some of them are called model-based, others are called direct, and the other are finite difference methods, right? And I'm going to very briefly go through them just to give an understanding. So model-based, derivative-free, sometimes people call it surrogate methods, right, is the following idea. So assume, again, that you have some kind of experiment, right? Let's say that you want to get, again, the optimal condition of some experiment. This is your X, so these are your experimental conditions. Assume that it's just one-dimensional, and this is your performance index, right? And let's say that you want to minimize this. So what you initially do is you grab and you do a few experiments, right? Data. But then again, you have data, but you don't really have this function, right? Like, again, these are experiments that you're doing. You don't really have the mapping of the function. Again, you can construct models, and sometimes that's the way to go, right? But in many cases, you don't have that, right? So what model-based methods do is, again, these are data points, is they try to build a function, right? So again, you don't have this function, right? But then what you do is you try to build one from the data that you have, right? And you have some kind of regression. And there's many types of regressions here. You can use things like neural networks, Gaussian process, decision trees, right? You can choose whichever your favorite method, and you create a surrogate function, and then you can optimize this function, right? So for example, if you wanted to maximize, maybe you want to go here, right? Because then this seems to be the maximum point, right? If you want to minimize, well, you're probably very close to a minimum already, but maybe you want to make sure that somewhere around there is the minimum. Now, the problem is that, of course, you know, there's many functions that fit this data, right? And obviously, I didn't put very crazy functions here, but you can imagine that, you know, generally, if you explore also in many dimensions, this can get quite complicated, right? So which of the functions is the best one, right? So these are some of the challenges that you have. Like, how much do you trust your model, right? It's relatively clear that, at least in the way that I've drawn it, here, right, the functions are all more or less aligned, right? But when you go outside, it's not very clear which is the correct function, right? So sometimes you want to also have what are called trust regions to make sure that your algorithm has a good prediction capability, right? So imagine that, again, you're doing this in a reactor. Again, of course, you would never do it directly on a full process, but assume that you're doing this, you know, you want your temperature to be capped or your pressure to be capped, right? So you want your model to be a good prediction, right? So areas over here, for example, might be off limits. Yep. Okay, so in the end, you know, if you do this kind of algorithm, what you want is a behavior that would look something like this, right? Where you start somewhere here and your algorithm makes its way to some optimum, which in this case I've just drawn over here, right? And that's the idea. That's what you would want your ideal model-based algorithms. Here, I've drawn a circle just around where I can trust my model, right? Because again, the idea is called model-based because you're building like a model or a surrogate of your true function. Now, there's many algorithms about this, right? One of the most famous one is Bayesian optimization, right? Probably most people here have heard about, which uses Gaussian processes, but there's many other things like using quadratic surrogates. Again, Gaussian processes are called general Bayesian optimization, radial basis functions, and many others. Okay. So later, what I'm going to talk about is how we apply these kinds of algorithms in this online book, and how we show that we can solve some, some very simplified chemical engineering problems. Okay, then other kinds of methods are direct, derivative-free methods, right? These are another classification. And these are also methods that are very well known, things like particle swarm, evolutionary algorithms, Nealder-Mead, like it's also called simplex, and so on, right? Which are basically methods that sample the function, right? And try to move around what people call intelligently, right? So it's not that they build a model, right? They don't sample and build a model. They simply sample a lot and they try to move intelligently. And different algorithms have different routines and so on, right? But again, the most probably well-known are things like evolutionary algorithms, particle swarm, Nealder-Mead, simplex, and so on. I won't go into too many details. The last one is finite differences, which I definitely will not touch. The idea here is that, again, many cases you don't have derivatives, right? Again, if you have derivatives, you should use them, right? That's simply what you should always do. But if you don't have derivatives, sometimes what you can do is try to approximate it via finite differences, and then you can apply your favorite Newton or quasi-Newton or Adam method, right? But these are methods are another thing on its own, so I won't go too much into the details. Okay, so again, we have many applications of this, right? And if people are interested, I can talk about it, but there's no question that there's many applications of this setting. And what I want to talk about is controller tuning, right? And actually, MATLAB does this. I think they use, I haven't really checked. I think they used either some kind of evolutionary algorithm or like a quadratic surrogate. But MATLAB uses this when you want to tune your PID controllers in Simulink, right? They actually use the procedures that I'm going to talk about now. Okay. So imagine that you have some controller, right? So you have your favorite PID controller, right? It looks like this. The idea is that a PID controller, right? You can think of it as a function, right? That given a state, right? Given the state of your reactor, maybe the temperature, the pressure, if you can measure concentration, the concentrations, right? It tells you an optimal action, right? And PID controllers generally do this based on how far away you are from some set point. Yeah? So a very simplified example, right? Imagine that you wanted to control the level of a tank, right? This is a tank, yeah? And assume that you have water going out here, right? And this is a bit stochastic, right? It has some mean value, but it has some variance, right? And you have a tank that slowly, it has an outflow, right? Which is stochastic. And you want to maintain the level of a tank at this value, right? So what would the way that you maintain it is that you pour water into it, right? But obviously you want to, sometimes you will pour more, sometimes you will pour less, such that you can maintain the level of a tank more or less at the level that you want, right? So what does a PID controller do, right? Again, maybe all of you know about this, but I just thought it's good to just have a general introduction. What a PID controller would do is it would measure the difference between the point that you want, so the set point, and your current point, right? And calculate the error, right? So this is the set point, the height set point, this is your current height, and then this is your error, right? And then what your typical controller would do is it would tell you, okay, the optimal action, yeah, what it will do is it will be proportional to this error, right? So notice that what this tells us is that if I am below my set point, this U is going to be higher, right? It's going to be positive, right? It's going to be more than zero. So it means put water, right? Because you're below your set point. If your set point is higher, right? If this value, the current height, is higher, your set point is going to be your error is going to be negative, right? And maybe in that case, whatever parameters you have, you want to say that you want this to be zero, right? Because you're already high, so you want it to drain. So you have basically an element which is proportional, right, to your error. Then you have something that's called the integral term, which simply, as errors accumulate, you have another term that tells you how to vary this flow. And finally, the derivative term, which tries to predict a bit ahead, right? So what's the trajectory? Am I decreasing my error? Am I increasing my error, right? And with respect to that, you also want to predict that. So this is a traditional PID controller and how you would more or less use it to level a tank, right? Just water on a tank. So this is a PID controller. And the idea is that PID tuning is all about moving around Kp, Ki, and Kd, right? These three constants, so that they are tuned correctly. That's what we call it, tuning. So they're tuned correctly so that you can, for example, level the water level of a tank given some input in the water. Yep. Okay. So how does MATLAB do it, right? Or how are we going to do it? So generally, what you have is you have some simulated environment, right? Which I'm trying to show here. Yeah. You give some values of Kp, Ki, and Kd, yeah, and you simulate your system. Maybe this is this line that I have here, right? And your initial values, whatever you decide them to be, of Kp, Ki, and Kd, they do not do a very good job, right, at leveling your tank. Yeah. So basically, what they do is they do a full simulation, and it says that it's not a good option, right? Sorry. Yeah, so this is just your full simulation, right? So generally, you integrate for a bit, and then you give the new set point to your PID, then you go back with your action and so on, and then this is this trajectory, right? So you didn't do a very good job at simulating it because you chose some initial values of Kp, Ki, and Kd, which were not very good, right? But that's normal, right? These are just your initial guess. But then what you do is you give these values to some optimization algorithm, right? Think about the values of that we had here, right? So before we had some objective function f. Maybe this objective function is how far you are, right? So this is your set point. Maybe your objective function is the sum of how far you are, right, at every point. And this configuration of the different k's, I'm going to just put k here, maybe gave you a very high objective function value, right? And that's one data point. Right, this is this data point over here. Yeah. Then what you do is you change. So this is the k at iteration. Okay, generally you will have a few data points, right? So you give a few different k conditions. So you give, a bit of what I was showing before. Maybe you give some of them like that. And then what your algorithm does is, again, it maybe builds a surrogate around it, and it tells you, well, actually, let's try this point over here. Right? Because it seems to be a very good point. So then this optimization algorithm gives back some some alternative for Kp, Ki, and Kd. You simulate it again, so maybe now it's this one over here, which is maybe much better. Yeah. And then again, you feed it back, and then maybe it eventually goes to one that is very, very good. Yep. But that's the idea, that you can actually do PID tuning. And again, MATLAB, this is what it does. It does PID tuning by simulating the system. So again, the idea is that you can think about this way, where your simulation is evaluating your function, right? And your algorithm is the one that decides, okay, what new points do you want to try it now? Okay, this is just also called simulation-based optimization or derivative-free optimization. These are almost the same as data-driven optimization, just known by different communities. Now, the idea is that, again, now driving back to the original topic, we designed a tutorial so that people would learn this kind of algorithms of data-driven optimization with PID2. The idea is that we modeled a very simple reactor, right? It's just a concentration of A and temperature. We show the code on Python there. Anyone can have a look. And then we show what the response would be if you have some arbitrary control, right? So this is the concentration, this is the temperature, and you have some arbitrary control actions. Yeah? And notice that this is where you want to track it. So you see that those arbitrary control actions do not do a terribly good job. Yeah? Then what we say is, okay, what if you do some kind of data-driven optimization algorithm? This algorithm is called PyBobigua, for example. We have the code over here, right? And we have the references in case you want to go into the actual algorithm. And then we show how you put this algorithm on a loop as well with the simulation and the optimization. This is, how the algorithm performs. So it starts here at a relatively bad point, and it slowly makes its way down to a good solution. Yeah, and this is basically the response that we get. You see that, for example, maybe initially the algorithm was going over here, right, which was not a very good alternative, and it slowly started making its way more towards a better response. In a similar way, Bayesian optimization is a very famous algorithm, right? A very, very famous family of algorithms, and you can also run it. So this is all for that you can either download or run it directly from Google Colab, and you also see how it's used to tune a PID controller, right? So here we assume that there's one PID to level the concentration and one PID to level the temperature, and again, you're able to move around this such that. So this is the control reaction, by the way. This is how the algorithm decides to control the level at different times. Okay, so that's for the this online book that we want to show. And now what I wanted to show is that we've actually done this in research, and we've actually constructed. We've used data-driven optimization, particularly Bayesian optimization, and particularly what we call multi-fidelity Bayesian optimization, to actually design a reactor with 3D printing and based on optimization on CFD modeling. So this work is on data-driven optimization now of expensive problems, right? This is my PhD student, Tom Savage. He's the one that did all the hard work here. And this was in collaboration with two people from Imperial, Professor Omar Matar and Nosheen Basha, who were the people that are experts in the CFD modeling. So the idea is, again, that we want to apply these data-driven optimization algorithms, right, to optimize some function, which we don't know exactly what it is. Again, there's many settings, but the one that I want to talk about just very briefly is about expensive simulations, right? So you know that we had this example where our simulation, right, was this maybe chemical reactor, and we saw how it interacted with some PID controller, right? And then we used an optimization algorithm to guide the parameters of the PID controller such that we would be able to, in the end, control some kind of process. Yeah? So we did the same, but in this case, instead of these, a couple of differential equations linked to a PID, what we have now is a full CFD model, right? And this CFD model takes anywhere between 5 to 12 hours to run. Yeah. And instead of that, and instead of having a PID controller, what we wanted to do is have an algorithm that automatically tries out different combinations, right, of how a tubular reactor should look like. And it assesses what is the best, basically, reactor configuration, right, or reactor design, to be able to maximize the conversion of some chemical. Okay, So again, the problem setting, the main challenge is that we wanted to optimize the design of some chemical reactor, but simulations were very expensive, right? In this case, they were around 12 hours of running time. So what we did is we used multi-fidelity Bayesian optimization. I won't go into too much of the details, but I'll try to paint the big picture here. So the idea is that we had an algorithm that would automatically try out different configurations, basically, or different ways to wiggle the tube of the reactor, right? So these were based on things that, I mean, humans can think of this, but basically an algorithm can mathematically abstract this and say, okay, let's try this thing, let's try this other thing. We use multi-fidelity optimization. What that means is that the full simulation, so if you wanted to get a very exact CFD simulation, that takes maybe 12 hours, yeah? But maybe we weren't interested always in doing a very expensive simulation, right? In many times, maybe we just wanted to run something that was less exact, right? But we could run in 20 minutes maybe, and gave us an idea of how good that that simulation or that configuration was, right? So this was all done by an algorithm that we got inspired by algorithms in the machine learning community and then applied it to our domain. And basically, this was the idea, that we had a Bayesian optimization algorithm telling us what was the next design. Yeah, so this design. And then we would choose this design and deploy it into a CFD, full CFD model. And the algorithm would also tell us, okay, this I want you to evaluate with a very high fidelity and take 12 hours to do it, or with a very low fidelity, right? And take 20 minutes to do it, and then maybe decide what do we want to do, right? And this is loosely based on things like information gain versus time of computation and so on. And again, I'm just here trying to draw a general pictures. If people are interested, we just released 2 preprints. One where we talk about the actual design of the algorithm and how it works, and all the code is available, and you can play around with it. And one where we actually explain from the fluid dynamics side, right, what interesting things we found, or that this algorithm found. And we actually, I always forget to add the picture, we 3D printed. So whatever our algorithm in the end told us, okay, maybe this is the optimal design, right? We 3D printed it and validated it experimentally, at a pilot scale, so not a super large scale yet. But we got very good results. Again, all the details are in the paper. But the idea of this is that data-driven optimization, we're actually using it in research. Again, MATLAB uses it for PID controllers, and it has many applications. And that's why we decided to release a small tutorial as part of this open source book. Anyway, that's the end of my presentation. I think it was, I don't know if it was a bit short, but thank you.
Hi, thank you, Antonio, so much. You are perfect on time, so that's fine. I will again kick off with a question. I think from an external viewer, it might be difficult to decide when to use reinforcement learning, because one might intuitively think that you should employ it always, but as we know that's not a solution for all problems. So do you want to give a few hints on when to apply?
So in this case, I think your example is very on point, because in this case because reinforcement learning can also be used for controller, reactor of controllers. But in this case, we decided not to use reinforcement learning and instead use this kind of basically static data-driven or Bayesian optimization. Because the problem is not, I don't want to say dynamic, because obviously control is dynamic, but the specific mapping is a static mapping. It's not a sequential decision-making problem. So actually, that's a very good point. We didn't put that on the book yet, although we have both sections, which have one on data-driven and another on reinforcement learning. But we should probably put a bit more insight into when to use one and the other. Because I totally agree with you. very common that people try to use these days reinforcement learning for everyone.
Okay, thanks. I think indeed that clears out a bit the picture. Thank you, Antonio, once again. In view of time again, I think we'll need to move to the next and final presentation by Richard Baur from Shell, and who is here today talking or making an introduction to Cape Open on behalf of the COLAN organization, which is, one of those initiatives that we truly need to make science and, in this case, software more open. So the floor is yours, Richard. Thank you for accepting our invitation. Richard, we can see your presentation, but we cannot hear you for the moment.
Can you hear me now?
Yes,
Oh, perfect.
we can see
Excellent.
The presentation is not yet in presentation mode, but the
No,
sound is
I will
working.
do that, and let me just also
Now we are all set.
get a point. Excellent. Thanks a lot for inviting me. Well, we talked a lot about open research and open science. I would like to focus now in the next couple of minutes actually more on open interfaces, and in particular on Cape Open. So the Cape Open are the interfaces which allows interoperability of process simulation software. This talk was arranged not only by me, but also by Oliver Koch from Linde Engineering, by Norbert Asprion from BASF, and also from Michel Pons, who is the heart and the soul of our Cape Open organization, which is called CIOLAN, and helps to develop actually these kind of standards. So in the next 20 minutes, I try to answer all the questions around Cape Open, where you find it, what does the interoperability do, where are the benefits, and why Cape Open is actually important. Let me just jump in. Open interfaces are important also for companies like Shell, Linde, or BASF, but also outside, and in particular in the domain of process simulations. We standardized actually the interfaces to different software components, and these standards are called Cape Open standards. So they define the rules and the interfaces which allow Cape, computer-aided process engineering applications or components to interrupt. I think it's very important here to realize that we are talking about interfaces, so a public standard which connects software with each other, but it's not actually open source or not a freeware. It's not a software package, Cape Open. It's really only the definition how the communication between the software packages actually works. The implementation of each of the interfaces on each side, either socket or plug, is up to the simulation software vendor, and that's usually based on well-known communication protocols like COM on Windows or Cobra on Linux. All of that in the standards is open, it's multi-platform, it runs on Windows and on Linux, but most of the applications honestly are under Windows, and it's of course also free of charge. What are the benefits of open interfaces? I think we need to highlight here three categories. First of all, it allows you to modularize your software package, and also it enables interoperability. So you as a user, end user, you can choose actually the best software tool for your current context, for your process simulations, for your digital twin, for your calculations with certain thermodynamics. The modularization also comes that actually you encapsulate your knowledge and your intellectual property in the model. At least you have got the option to do that. But also it allows actually to do some rapid model development. I'm saying this because you can, for instance, if you have got the interfaces standardly defined, you can use Python, MATLAB, or any kind of scripting language to sketch a model and immediately plug it into a flowsheet simulation environment without worrying too much how the communication between the software environment, so the flowsheet, and your model should work. That should come and work out of the box. Similarly, you can develop for your specific property package, let's say, for multiple platforms. So you can develop on a platform A, let's say, in Aspen Plus, and then still you can have got a customer with Unison Design or with Pro2 or any kind of other flow sheet. Since the communication is actually exactly the same, you get this flexibility, and it also allows to be much more efficient in plugging in the thermodynamics which we want. In practice, often this means that you have got in-house models which you would like to run on these different simulation engines, because they're also used in different contexts within the company. Most important is that actually with standardized open interfaces, you also guarantee consistency. You can use the same thermodynamic package for different software packages. And we will see a couple of examples later on which exemplifies this. And that also means you don't have to manually actually transfer from one software package to the other one information. An obvious advantage, of course, is that if you have got only one interface, then you save costs and overhead because your interface is standardized. So that's where the standardization makes your developments cheaper, faster, and actually you've got much lower maintenance costs. So what Cape Open interfaces are there? I already talked about flow sheeting. So these are process modeling environments. And in these process model environments, you can connect actually via Cape Open interfaces to different model components, process model components, we call it PMC. This is a little bit the jargon which we have within Cape Open. So that could be a property package which does vapor liquid equilibrium calculations or calculates the density or whatever you can think about thermodynamic calculations. And you also can have good unit operations which can represent acid gas removal unit or hydrotreater or any other kind of things, heat exchanger, which you then can plug in the process modeling environment. As I mentioned before, there are also generic modeling tools, like, for instance, Excel, GAMS, Python, MATLAB, Scilab, which also can function if you have got the right wrapper around it, and this is available from some software supplier. Then you can make actually a unit out of it and plug that into the process modeling environment, which allows you to do some rapid prototyping of what you would like to model. The other way around also works. You can put a thermodynamic package in MATLAB or Scilab or Python and do some calculations on top of it. You can do some model optimization, what we heard in the talk before, or monitoring. You can do some reactor design. There are a variety of applications which are available. Now, I already mentioned about thermodynamics and unit operations. These are the most mature Cape Open interfaces, and these are also very frequently used process model components. Less frequently are, for instance, the interfaces for petroleum fractions. We have got a very small example later in the tour for chemical reactions and flow sheet monitoring, as well as for physical property databases and numerical solvers, or even for optimizers. Their interface is defined, but they are not that frequently actually used. So at this point in time, most of the applications are around thermodynamics, unit operations, and maybe we can say also flow sheet monitoring, which becomes in times where you do actually work with digital twins, where you much more want to be able to do connect rigorous process models with data acquisition and analysis tools may become in the future much more frequently used than it is at the moment. Here you have got a list, and the list is only a selection, but it shows you actually all the flow sheeting environment or process simulation environments which are Cape Open compliant, where you can plug in a Cape Open unit and simply run it out of the box. And you have got here also a list of the thermodynamic property packages where you can do the thermodynamics in your process simulation environment, and unit operations which are available either commercially or as freeware. I don't want to go over the individual names here, but I think we also should remember often many people, universities, but also people in Shell have got their own in-house packages, which they also would like to connect to the different simulation environments. These standards are maintained by a small organization, and that organization is CEOLAN. It consists actually out of 6 full members who pay a little bit more membership fee than associated members, and these are Air Liquide, BASF, BP, Dow, Linde, and Shell, which are more or less also forming the board of that organization. And then you have got the software vendors, as well as academics who are member as associated member, and in particular the software vendors also contribute to the finances of CEOLAN with a smaller fee. In total, we have got around 100 members. This organization has got special interest groups, and there are 4 or 5 active at the moment: the thermodynamic and the unit operation special interest groups, which has got members from the operating companies, so from the full members, but also from software vendors. And in these special interest groups, the standards get discussed, and they are getting actually written in a textual form. They will be then also distributed on the internet. You can go to our website, www.ceolan.org, and there you can find actually examples, but you also can find the textual specification. You can download them. Everybody is welcome to join our organization. In total, we also have got around 24 individual members. But one of the requests we have, that anybody who is applying for this organization should also have got a Cape Open related project. Then we will accept actually this application. The organization these days also has got some software development projects. We are developing at the moment a test suite, which allows you to test actually the Cape Open compliancy, and which may later on also lead to a certification scheme. But we also work on a middleware, which is called Cobia, which facilitates more or less the implementation of Cape Open interfaces. Let me give a small example how that works. Let's make a very simple example. We say that we would like to run multi-flash within MATLAB. Now, what CEOLAN does is providing the textual specification for the thermodynamic Cape Open interfaces. So in practice, in this document, we see what kind of interfaces need to be defined, what kind of functionality you can get. For instance, the isothermal equilibrium routine defines more or less how you can get a vapor-liquid equilibrium from the property packages. You also have got other interfaces, like how do we identify the property package, or if there's an error, how do we communicate that to the simulation environment. Part of the textual specification is also that we have got use cases. And here, for instance, we have got the example of getting a density calculation done. So between the MATLAB and Multiflash sits a material object. That's a kind of storage. So on this material object, you can set the temperature, pressure, composition. You can make a request. Look, I would like to get the density calculated. That request will be then passed on to Multiflash, and Multiflash will take the temperature, pressure, and then makes the calculation, sets the density, and at the end, actually, the density gets exposed to the users. To have the sequence clearly defined helps to be actually have a good interoperability between all the software package, not that there is a misinterpretation how actually the calculation sequences should be. Now, if we look actually on the software side, so as I said, the software vendors have to implement that. That might look much more complicated because you have to really implement all the interfaces in COM or CORBA. We, at the moment, developed actually also COBIA, our own middleware, which you then have to install, but it's not required actually with the standard COM interfaces. Cape Open works perfectly. And there's also actually a translation from COBIA to COM to ensure actually interoperability. Even so, one software component only talks to COBIA, and then COBIA talks to COM. But the point I want to make here is, even though it looks very complicated, if you're using COBIA, then Amsterdam, for instance, has also a COBIA wizard, which helps you actually to produce the default classes and gives you a kind of template where you only need to fill in and program the essential parts, which are really customized to your unit operation. In general, we believe that actually using COBIA has an advantage in performance. We demonstrated that COBIA also runs under Linux and under Windows, so it's independent of the operation system. And it's much easier with the help of these wizards to program. Now, the end user doesn't have to bother about that. The end user sees something much more simpler. And that depends also very much on how the implementation on the socket side is. But here we took the example from Jasper van Baten, who made actually the socket for the Cape Open property packages in MATLAB. And then you just request actually a handle to the property package, here water and butene. You define a vector of the compositions and a vector of the pressures. You would like to have the phase diagram drawn, and then you loop over the pressures, and you call the equilibrium calculations routines, which for a vapor fraction of 0 or 1, which gives you the bubble or the dew point. A couple of lines, and you're done. And behind the scene, actually, the communication takes place via Cape Open interfaces. Let me go through some of the examples from our companies. And I always put here, if you're interested really into the details, some of the references, please have a look. And there you find more about these examples. I try to summarize these as good as I can. Hopefully I don't miss too much. But these slides are from Ralph Knott, and it's an example from BASF. They're like we do in all our companies, we use actually process simulation environments to make the heat and material balance, which is the basis for the design. And this the process simulation environments are actually connected to an integrated software, which allows you then to generate data sheets or process flow diagrams or PNIDs, hydraulics, reliefments, simulations, or whatever, some other kind of summaries. In the example where Cape Open turned out to be extremely useful, they looked here at the unit operation which is called OAS. It's a gas rating software package which has got a lot of IP from BASF in there, and you must imagine acid gas removal unit is not a simple unit operation. It's actually quite a complex, can be quite a complex subflow sheet. But in this example here, we look at the sulfur removal of natural gas and also the CO2 removal via the acid gas removal unit. So using OAS, the proprietary gas treating technology from BASF. So once H2S and CO2 is removed actually in the regular flow sheet, you still remove the water, and then actually you can cool down your natural gas to minus 160 degrees C and liquefy it. Now, since these acid gas removal units are quite complex subflow systems with complex thermodynamics, they're usually running also on their own server. And previously, there was always some manual interaction in order to connect the flow sheet with these dedicated calculations. The OAS software package, as I said, sits on the server, and with having actually the Cape Open interfaces, the flow sheet itself can connect to the OAS BASF server, can do their expensive and important calculations before it reconnects actually to the flow sheet. So the circle about connectivity between two different and separated software entities is ensured, and this leads to, first of all, savings in time and resources on money. It's much less error prone, but you also get a consistent heat and material balance, and you can much more efficiently then generate actually technical data sheets and do the further equipment design. Another example, now small example from my little world. I'm working in hydroprocessing. We do hydroprocessing of vegetable oils, pyrolysis these days, but of course we're also taking care of our hydrotreaters and hydrocrackers. And we internally have here for our refinery models our infrastructure where we can connect to our Shell proprietary interface different process model like the hydrotreater, hydrocracker, or cat cracker, or any kind of other refinery model which we in-house have. And that actually further can be used either in a standalone to do some kinetic estimates for catalyst sales, or we can connect it to real-time optimization. Or, and that's where Cape Open comes into place, we can actually use the Cape Open interfaces to connect to the process modeling environment. In our case here would be, for instance, Pro2, and run actually our models within Pro2 using Cape Open. The special thing if you deal with refinery, you need to use actually, you're not talking about pure components, but you're talking about lumps, and lumps can change their properties. For instance, the sulfur content in the feed with a hydrotreater where you want to remove the sulfur is of course much higher than actually at the outlet where you have got then a sulfur-free diesel. And the example here shows that. I think here the take is also, since we have got Cape Open, we can actually use our own models more consistently in the simulation environment. It becomes less error prone, and so we are getting rid of all the manual input-output mapping. Now, this is an example which I like the most. That comes from Linde Engineering. Also an example where you make use of open standardized interfaces like the ones we have from Cape Open. They also have got process simulations. They also do process equipment size, equipment sizing, and they use for that specifically a software package for the processing, which they call Process and Equipment Specification Platform, where they make advantage also of HDRI's Exchanger Suite, which is a third-party package, and they connect that in the past via property tables. And the property tables are generated by their own thermodynamic package, which is called GMPS. But it's a very time-consuming and manual procedure to do that. Once you have got the property package, you get with the Exchanger Suite actually the heat exchanger geometry, and you can feed that back to the specification platform. Now, Stefan Gebel got aware of Cape Open, and without any further or with very little effort, it was possible to directly connect the Exchanger Suite with the property package, and so get rid of this manual generation of the property tables, and that led to a much more efficient workflow and helped and also more consistent workflow. So here you see, just because both software packages were already Cape Open compliant, without problems you can connect these two with each other. His feedback was very positive. He didn't see any negative points, but only actually the plus points with being able to put together the software which you need in order to solve your problem in an efficient manner. Last but not least, I would like to highlight actually that Cape Open is also frequently used in academia. There are a lot of initiatives which adapt Cape Open, like for instance the freeware packages or open source package like DWSim for Daniel Wagler or Mosaic for the TU Berlin. But there is also, for instance, a spring-off based on the ideas of Cape Open, which is called COCO, the Cape Open to Cape Open simulation environment, which you can download. And what I like very much is actually the initiative Cape Open and the ideas of open interfaces, also picked up by Klaus Müller from the Cape Town University, who uses that explicitly in his teaching programs. And all of these four have got common that they got at a certain point the Cape Open Award. This brings me to my last slide. You saw this slide before. It's actually the benefits of open interfaces and also the benefits of Cape Open. Don't want to repeat it too much. Just want to highlight the three examples from our three companies clearly showed what is the advantage of modularizing and interoperability. It's simply that you use the software which is best for the purpose, and you can combine that. And also you can encapsulate actually IP if this is necessary. I think we also showed that consistency is ensured by using open standards and also open interfaces, and that the savings and the costs of standardized interfaces, that the cost and the overhead are reduced by using standardized interfaces. Yeah, with that, I would like to conclude my talk, and please ask any questions you would like to.
Okay, thank you so much, Richard, for your very nice talk. I was wondering, before we get any other questions, I mean, you heard Theo talk and the potential of transformers for converting one type of information into the other. I mean, have you looked into artificial intelligence to take care of some of these tasks, or is that something out of the scope of Cape Open? I mean, interfacing tasks, of course.
we thought about it actually. I mean, that comes also to a certain extent in the context of the flow sheet monitoring, right?
Mhm.
Where you extract actually information about the connectivity, about unit operations and other kind of things. And obviously the other way would be around. Why not having interfaces in order to generate actually flow sheets, right? And that's something you can then also think about connecting with AI or with any kind of generating algorithm, so that you say, okay, I'm going to train actually on the basis of, yeah, I train a neural net or a AI machine learning, and I evaluate actually the different combinations by regenerating these kind of flow sheets and evaluating them according to an objective function. That could be potentially where the connectivity comes from.
Yeah. Okay. Thank you. I think again, in view of time, we'll move to the final remarks. Thank you so much, Richard, for your time and
You're welcome.
very clear presentation about Cape Open. So I think this brings me to the summary indeed. So I think interdisciplinarity is clear from these 4 presentations, that we can learn much from each other. So interdisciplinary, putting open science together will be key, because some fields are further on one specific aspect than others. So we do need to talk and to learn from each other. I think it's also clear from today that there are many initiatives. The whole landscape is not clear, the whole infrastructure is not built, but there are many initiatives in doing so. As I also presented to start with, even initiatives aiming at making a coherent whole of these individual actions being taken. So I believe that indeed in a few years, the full infrastructure to make open data and open science possible will be there. We also saw many examples of applications, and I think, I mean, with all the potentialities of machine learning we have all heard about lately, I don't think we need to further dwell on this. It's clear that if open data is there, open information is there, we'll make it useful in one way or another. The last word is for the role of community-driven action. So Cape Open is one of them. Companies and academics got together to produce this interface and improve interfacing between previously non-talking software, if I could say so. So community has a strong role to play here, because we are still building this infrastructure. So as a community, let's take our role and make sure that chemical engineering does step up into open science. With this, I will give the word to Laura from the EFCE working party. Laura, shall I share the screen now, or?
Yes, Pedro, that would be nice. So first of all, let me thank again you, Pedro, for being one of the main organizers of this event, and Martin, of course, who took care of the whole practical organization, and also our speakers who dedicated a whole afternoon plus the preparation time to this event. There are 3 main messages I would like to give, very short. The first one, you see it on the slide. It's a small survey, like takes 2 minutes to fill in, because we would like to arrange a live event on open science for chemical engineering in the first half of 2024. We would like to understand from you and the people in your network. So it would be great if you could share this link that Martin just posted in the chat, to understand how could we make this event useful to you if you're interested, if your network is interested, and how to best arrange that. So it would be very much appreciated if you could take the survey and share it a bit with the people in your network, your students, your colleagues, and then maybe see you at this event next year. The second message is really about the fact that these webinars are recorded. They will be posted on YouTube. You already heard that. Please use it. Use it for teaching, use it for knowledge sharing, because as you can see, all our speakers put a lot of effort in preparation for this. There's a lot of knowledge being shared, and it would be great if it could go beyond this Zoom call and reach audiences of students or especially early careers professionals who are also the ones who should drive further chemical engineering in general and open science in chemical engineering as well. And the third very short message is to remind you that this webinar was organized by the early careers section, meaning students who are finishing their studies, or PhD students, or people in their very first years in their long career. If you are one of those, or if you know some early career chemical engineers, please get in touch with us on the EFCE website. There is a section dedicated to us, and let's discover together how we can further contribute to spreading chemical engineering knowledge throughout Europe. So with this, I can conclude, and I don't know, Martin, if you have an official farewell word from EFCE.
Hello. No, sorry, not something special from EFCE. Just to thank all the speakers and also all the participants, and just to remind to the participants that the video is recorded, the webinar is recorded, and the video will be available on the EFCE YouTube channel. Okay, that's all. Thank you.
Thank you all.
Bye.
Bye. Bye-bye.
All the best. Thank you.